For those of you who don't know me, my name's Yonik Seeley. I created Solr, a long time ago now. I helped co-found Lucidworks and had some other, interesting journeys along the way, and I'm now at Cloudera with the awesome search team there. I'd also like to point out that Apache Solr was accepted into the Apache incubator in January of 2006. So we're rapidly coming up on Solr's 10th year anniversary as an Apache project. So, mark your calendars. There should be some good stuff next year. So, Solr for analytics. Why are so many people using search engines and Solr specifically for analytics stuff, especially for big data in the Hadoop world? Well, it turns out search is a key component of a lot of big data problems. A lot of analytics problems, they start with search. It's like, how do you define the set of things that you're interested in to then go and compute other interesting metrics about? Search is often involved in the mix somehow. And it turns out people have had a lot more success adding analytics to a full-text search engine than doing vice versa, than trying to add good full-text search to something like a traditional database. That has just never seemed to work out well for people. So another way that you might think about doing it is like, oh, use full-text search engine for your full-text search part and use something else for your analytics part, right? The problem comes in is when you're talking about real-time analytics. And when I mean real-time, I'm not talking about like high-frequency trading or anything, but real-time interactive. From the user's perspective, they're clicking on a mouse button and they want something back in a reasonable time. We normally shoot for things like sub-second. And so if you're looking at external integrations, the most natural way to do that, what some people try to do, they query the search engine, get millions of IDs out, and try to shove it into a different system to do, compute other interesting things about it. Doing that in any kind of interactive time frame, sub-second, is very, very challenging. So it just becomes a natural question. Okay, I need good full-text search. Now that I'm already in this system, now that I'm already in Solr, what else can I get it to do? Now, if we look at Solr and Hadoop specifically, Solr's carved out a pretty good spot in the Hadoop ecosystem. If you look at all the top Hadoop vendors who have chosen to integrate search, they've all chosen Solr. And I think part of it's because we've had that historical focus on interactive response times. We all want everything to be sub-second if possible, or at least examples of these things to be sub-second. People, you get faceting, yeah, it works sub-second, and then people throw it on 40 or 50 fields. It's not sub-second anymore. But at least we want some of it to be able to be sub-second. We've also had historic focus on faceting, which is, if you think about it, it's a simple form of analytics. It's like a subset. And we have another advantage we have is just our high-performance indexes. If you're going to do full-text search, you have to have really good index technology. And one key is, if you have really good index technology, it's applicable to a lot more things than just full-text search. It's also applicable to metadata and other types of data. So just as a little review about what an inverted index is, it's basically, we call it an inverted index because terms point to, or words point to the documents containing those words instead of vice versa. It really is just an index, but we call it inverted index for some reason in IR. So in this example, we look up the word hood, and we see that it's in document number 0 and document number 1. Now, there's lots of other information that we can also conditionally index. For example, the number of times each word appears in the document, and even the exact number, the exact positions that the word appears in. So we can do things like phrases. So obviously, if you're going to index the position of every single word in every single document in your corpus, you need very, very good indexing technology. And that's what we have with Lucene, and that's really a competitive strength. We also have a buzzword lately. It's columnar storage with doc values. So if you know Lucene and Solr, stored fields are stored as a blob. It's here's your ID, giving the stored fields back. You just get like the list of them back, and that's not good for analytics, because if you want to run down all of the values for a certain field, you just have like really horrible locality, and it just doesn't work well at all. So of course we've never tried to do anything like that in Lucene Solr. What we did in the past was basically create an in-memory column. If you wanted to sort on a field, we'd go through the field cache, create an in-memory representation, an in-memory column based on the index terms, basically uninvert the field again, and then use that. So doc values is really the index time equivalent. Doc values will build a column where all of the values are just like adjacent to each other, so you get really fast random lookups and just great locality and highly compressed still too. So we'd have things like prefix compression, delta compression. It's almost like having a mini little parquet, if you know what that project is, embedded in Lucene. Another key advantage here is that its doc values are mostly off heap. Because they're done at index time and it's a file that's written, it can be memory mapped in, and it's not on the JVM heap. And the advantage there is that helps with the memory pressures, and if anybody knows with really large JVM heaps, you run into really large garbage collection pauses. And of course, these things can be chosen on a per field basis. So it's just like really great for analytics. And you see a lot of the new systems coming out, especially in the Hadoop ecosystem, they've moved to this column format. Well, we already have it. So another advantage, I think, and why search engines are so good at analytics is how the index is structured underneath the covers. We have like a multi-segmented strategy where an index consists of multiple segments, and these segments are write once, read only. Once we write a segment, we don't change it. And so one thing that this means is we can very effectively cache things on a per segment basis. If you go and you add a couple new documents to the index, really what that does is it creates another little segment off to the side, and then a descriptor to point to that segment as well, and include it in the overall index. And if you get enough of these little indexes, little segments, they're merged into a bigger segment. That's how we avoid getting just too many of them. But so we can cache, and some of the bigger segments, those caches will be valid for quite some time, because we can, it'll be a long time till we hit merges. The other advantage, it's almost like a disadvantage, but you can turn it into an advantage for search applications, is that we have point-in-time searchers, right? If you go and add a document to the index, it is not automatically reflected. You sort of have to choose how often your view of the index is changed. So for some applications, they might want it like, really fast. Every second, I want to see the new data. Some applications, 30 seconds is fine. Some applications, they might, re-index all of their data like every day, and after that, it doesn't change. And so there's some other data that makes sense to cache at the whole index level, and we can do that for the duration, that our snapshot is valid for. And so just like a combination of being able to cache at these multiple levels gives for, although it's not quite real time, it gives you very fast interactive queries. So just a little refresher of faceted search. This is an example of faceted search. I just searched Amazon for Android tablets, I believe. And the search results were on the right, and the facets were on the left. And facets are just like breaking down the data in various ways, right? So, it broke it down by the display size, the average customer reviews, features, and price buckets. And then, like any good faceted system, provides a way to select various categories and drill into your search results to refine them. So I want to switch now to talk about what I've been working on more recently, the new facet module. Well, so first off, Solr's had faceting from the beginning. Why a new facet module? Well, there's been a lot of functionality developed over time. Statistics, grouping, joins, the faceting, and not everything has always worked well with everything else. You know, sort of like, you know, they're written as separate components, and some things worked some with other things, but so for example, grouping has never worked that well with statistics or hasn't worked at all with statistics. The same with faceting. There's been some recent work to try to join these together, but it really wasn't done that way from the beginning, you know, with that goal in mind. And so, so I decided to try to, like, you know, rethink this, create a new facet module that would really be the platform for like adding all of this functionality together and usable through a coherent API, which I'm calling the JSON facet API. So here's sort of a logical view of faceting. So we start off with our domain. Domain is just like a set of documents. It's the things that you want to calculate things over. And basically, the root domain is defined by your query, the query and the set of filters, and that's how you get this starting point. And then you can use facet commands, and in this case, I have facet command A and facet command B, that take that input domain and produce multiple output domains by any number of methods. And we also have a notion of subfacets. So really, any domain is like any other domain. We can have like subfacets, facet command C, that take the result of every domain coming out of facet command B and further split it up into multiple domains. So you can really see how you can just continually slice and dice the data this way. And we can also call these facet domains. We can also call these facet buckets. And once we have that, we can add statistics or facet functions that basically calculate something interesting over a given domain. And so in this example, I'm asking for the average price and the minimum number of units across the root domain. And out of the domains that were produced by facet A, I'm asking for the sum of field X and the unique number of things in field Y for each of the domains produced. So another cool thing that we can now do is also sort by any given statistic. Faceting has traditionally been about document counts, and you can only retrieve document counts, and you can only sort by document counts. So it's really important to be able to sort by something different because you can't always do it on the client side. Some of these facets might produce millions of domains, but you really don't want to return millions of domains to the UI for any number of reasons, right? You really only want the top whatever, like top 10, by some criteria. Now in the past, that criteria was just sort of fixed for you. It was basically, well, you could ask for sorted order, or you could ask for, count descending, and that was it. And now we can ask for Solr to basically sort by any given statistic that you can think up. So here's a current overview of what we have for facet functions today. So we have the usual that you'd expect, sum, average, sum squared, min, max. If you look at max, you'll see that it's an example of how we can do things not over just fields, but of functions of fields. Unique gives the number of unique values in a field. HLL is an interesting function. It's hyperlog. And that's basically a way to do a distributed estimation of cardinality. Because it's not really possible to do exact cardinality in a distributed way without streaming all of the values to a single aggregator. So hyperlog is a way to sort of trade off memory and accuracy. And so, but you do know you can calculate the error bounds and how much you can sort of tune it and say, okay, I'm willing to use this much memory, and I know that the error is going to be this much. Along those same lines, we have percentiles, which uses Ted Dunning's T-digest algorithm to estimate distributed percentiles. And then something that is not yet committed, but I'm currently working on, is TopDocs. And TopDocs is really the first step towards unifying grouping into the new facet API. top docs will just give you, for every facet bucket, the top documents for any given query sorted by however you want it. And so if you know about grouping, this is very much like grouping, except I haven't done the code yet to like sort domains with respect to each other based on the top document in each group, if that makes sense. I think you sort of have to know grouping already to understand what I'm talking about there. But it's coming along. It's first steps towards really unifying grouping in with this. Let's wait until later, just to make sure we have time to get through everything. So let's look at a simple request and response in the new JSON facet API. So it's really the simplest thing. We just have this new JSON.facet parameter, and we are asking for the average price and name it X, and the unique number of brands, name it Y, and you see that's what we get back on the right-hand side. We also get back count, which is just the number of documents that were in our root domain. The root domain defined by the documents that are query matched. Sort of as an aside, we can also ask for, we can also do requests to Solr all in JSON now. So in this example, the whole thing is just one JSON body, the whole request. And so we have our query, filter, offset, limit, sort. When we get down to facet, we don't use JSON.facet because we're already in the JSON domain. It's sort of a way to, there's like something that I call smart merging. If you have a query parameter called JSON.something, then that essentially sticks it in the JSON domain. So it'll, if you had a query parameter called JSON.query, that would actually like override the query in the actual JSON body. So here's the different types of faceting that we can do. We have a terms facet, also known as a field facet. That's like the most basic type of facet we have, and the most common probably too. It's just based on the unique values in a field. So that would be like, if you had a colors field, if you had a category field, things like that. Range facet is pretty self-explanatory, I think. It just creates ranges on either date fields or numeric fields based on ranges. You go to start and end and a gap, and it creates buckets based on ranges. And query facet is interesting. It basically creates a single bucket of things that match an arbitrarily complex Lucene query. So whatever you can express as a query, you can sort of refine your data based on that. And of course, any of these can now be nested under any other facet type. So it doesn't matter how the domain got created. You can further split up that domain based on any of these facet types. So here's a simple terms facet example. So we have our JSON.facet, and we call the facet shoes, and we say the type of the facet is a terms facet. It's on the field shoe style. We're sorting by X descending, and X is defined in the facet block within that facet, and where we say, X is the average price and Y is the unique number of brands. And then if we look at the response on the right-hand side, it very much mirrors the request structure. And so we have the count of documents that's just in the root domain, and then we have our shoes facet, and it has a bucket list. And the extra thing we see from in each bucket is a val, and that's just basically the value for the bucket. And basically, it was the value of the shoe in the shoe style field that produced that bucket. So pretty straightforward. So for a subfacet example, how that works, I've sort of like highlighted just the differences. This is like our previous query, except in addition to X and Y, we've also asked for a colors facet, which is a terms facet on the colors field. And we just put it right in with our X and Y right after it. And then likewise, in the response, we get back for each facet bucket, we get back our X and our Y and the colors facet, which has its own bucket list. And since we didn't ask for anything else, we just really get back the count along with the bucket value. So let's look at a simple BI use case I sort of just like made up. This is sort of like a bookstore company that has like multiple chains, Amazon, Houses and Royalty, and Books R Us. And they have this, their BI dashboard to see, where their revenue is coming from. And so the top chart is revenue over time broken out by genre, book genre. And then the graph below that has revenue over time broken out by the bookstore chain. And then underneath that, we have things broken out by, over the last whatever time period is interesting, by genre, first of all, and a total amount of revenue that each genre generated. And then under that, for each genre, we have like the top authors and the amount of revenue attributed to them, as well as the top books and the amount of revenue. And so you can sort of see already the differences between this and traditional faceting. Everything we're working with here is a derived value revenue instead of document count. And you could sort of imagine how this could work. A lot of the stuff in blue could actually be links, and so you could click on things to like sort of, again, drill down into your data and further like, sort of refine things and discover, where your revenue is really coming from or problem spots. So here's how you'd implement this with the new JSON facet API. At the top in the boxes is sort of like the logical view. And so we just start off with a range facet on the sale date, because we're doing things over time. We're bucketing over time. And under that, we nest two terms facets, one on the genre field and one on the chain field. And then hanging off of those two facets, we're asking for sum of sales on each domain generated. And so on the left-hand side is the JSON that sort of corresponds to the logical view. And so this is like the first time we've seen like the actual syntax for the range facet. And so we've said, okay, we're naming it date breakout. The type is range. The field is on sales date. And we have our start and end and a gap. And the gap is in like date math. So we can say like +1 month. And then we have our facet block that defines the subfacets and statistics. And we have a top genre and the by chain, which are just straightforward mappings from our logical view. And that gives us all the data that we need for these charts. So coming to the bottom view, this is how we would implement that part. Again, so for the logical view, we start off with a terms facet on genre. We ask for sum of sales on that, but then we also have two subfacets on the author field and the title field, and also asking for the sum of sales and naming it revenue. So here, the thing to notice is, again, it's pretty straightforward, but both top authors and top books, we are sorting by revenue, by our derived statistic. So let's take a moment and look at performance, one of my favorite topics all the time, because APIs are all nice and well and good, but you want things to be fast, right, and high throughput. So recently there has been some, I guess I'd call it parallel work done in what I call the legacy facets, hanging statistics off of pivot facets. And so that request is on the left-hand side. And I benchmarked that against the new JSON facet API, the new facet module, and that request is on the right-hand side. And so these two requests are asking for essentially equivalent things, but you have to do it through the pivot facet API if you're using traditional Solr facets. And so here are the results. And so this is essentially, if you break it down, what it's doing, it was faceting on a multi-valued string field, and then calculating the average for each facet bucket, or for the top facet buckets. And it looks like the new facet module is roughly 3 times as fast for this. Now I think most of the performance increases were due to the statistics. I think the existing Solr statistics module is probably pretty slow, because I think the faceting has always been pretty fast. So if you just compare just faceting, I think they're probably pretty comparable today. But it's when you add in other things like statistics, you really start to see the big gaps, and we really pull away at about 3 times as fast. Another really interesting metric was looking at the memory produced by both of these requests. Our legacy facets, basically it was the same test as before. I just ran it multiple times and looked at the total garbage produced. And it was 73 gigabytes by the legacy facets and 4.5 gigabytes for the new facet module. And I think we can do even better, but it's already just quite a drastic difference. So who here has heard of block join? Okay, good. More than some other conferences. That's what I would expect. So I've also done some work on block join, so I'm going to go over a little bit of an overview of the current how stuff currently works, and then how I tied that into the new facet module. So basically, indexing nested documents. In this example, I have books, and I have book reviews. And instead of fully denormalize them all, I've used the nested documents feature to index them as a block. And so what that does at the Lucene level is it puts them all right next to each other in the index. And if you know that your parent and child documents are all right next to each other in the index, you can do some cool things mapping from parent to child or vice versa in a very quick way and very cheap way. It's you don't have to have any pivot tables. It's very inexpensive to do. And so, so in this example, we have books, and then we have book reviews that are the child documents. And if you look at the index, what actually gets indexed is that we have the child documents indexed first, and the parent documents are indexed after that. So the parent documents are indexed last. We actually could have done it vice versa, but we just had to pick one way, and I think people were thinking of child to parent roll-ups would be easier if we index the parent last. But as long as we're consistent, we can still work with it. So how you actually index these things, this is just one example of how you actually index nested documents. If you know how to index something in JSON, it's just field type, field value, and now we just have this special tag called child documents. It's an array, and it just has the subdocuments. And so when you send this into Solr now, it'll just all be indexed as a block in the index, kept contiguous, won't be split up, indexed atomically, and we can then do block join stuff over it. So here's an example of block join queries. So the first one, the top one, if we want to find review objects mentioning Epic, but we want to limit those reviews to books published by Tor, then we have to do some joining, because the review objects themselves do not have book information like publisher. And so really, we want to look at the FQ first, and we want to read it right to left. So we start with publisher : Tor. Okay, so we're finding books that were published by Tor, and then we map all of those matches to the child documents. And so this essentially creates a filter for all comments on Tor books, or all reviews on Tor books. And so then we can just for the query, it can just query the comment field directly, and everything just works from there. So the magic is really in the filter. And so mapping the reverse way, if we want to find all books published by Tor with the review mentioning Epic, so again, we start off with our FQ, read it right to left. So we search for comment : Epic. Okay, that gives us review objects. But we really want book objects, so we map it to the parents. And so that gives us all books that had a review that mentioned Epic. And then our query just searches for things on the book objects like publisher Tor. So now this is how we worked it into the new facet API. If I wanted to find the number of books that I reviewed broken out by genre, here's now one example of how I can do that. We have our normal terms facet, but now we have this new domain keyword. And it's called domain because we're switching the domain. We're no longer just sort of like narrowing or picking out of, normally you start with a domain and you normally pick a subset out of it. That's the normal way. This type of operation can completely change the domain that you're working over. And so what this says is, okay, well first we have our query. And I'm searching for review author Yonik, so I come up with reviews that I wrote. And then we go to the faceting, and we look at the domain first, and it says, okay, the incoming domain is child objects, map them to the parents. And then after that, do the facet on the genre field, and it's a terms facet. And so that'll actually give me back books broken out by genre that I've reviewed. And then going the reverse direction, if I wanted to find the top reviewers for sci-fi and fantasy books, so I query on the book objects, and so I'm querying for like, genre, sci-fi, or fantasy, and so then I have my input domain that consists of book objects or parent objects, and then what happens is before we do the facet, this domain is telling us map to the children, which are the reviews. And so at that point, we'll get all the reviews of the books that were selected by the input domain, and then we'll calculate the terms facet over the review author field, and we'll get the top reviewers. And so you can see, this is pretty powerful stuff, and in the future we'll be able to combine it with a lot of other cool things, like the top docs, and there's actually something that I just committed last week, which is a graph operator. And so next I'm planning on, I don't even have slides for it yet, but it would be another domain operation where you can say, okay, yeah, we're not even doing a join now, we're doing some sort of like graph traversal. For each facet bucket, do a graph traversal and then facet on that. So pretty, I think there's some pretty cool stuff in the works. All right, and it looks like we have time for some questions. Yes?
I have two questions. The first one is regarding to the new facet. So for the new facet, it's a support the shared parameter. I'm asking that, especially for the Yonik, since we used to use a group, not two groups, that one needs to all the term group the same form. So this, okay, so that's why. The second one is for the BI. For the BI. So business analysis. So basically, the situation is currently already found the BI tool like the Power BI, table, Excel. All they working with ODBC on cycle. So do we have any plan to support the ODBC on cycle?
Okay, so the first question was about grouping.ngroups. There is a parameter that I didn't show where you can, for each, for a field facet, you can ask for what were the total number of buckets. And there's also other things you can do, like you can have a missing bucket. It's like, create a bucket for documents that didn't have a value for the field. And there's an all buckets where it's like, yeah, just like do the superset of all the buckets. I'm interested in everything. And there's I forget what the parameter name is, but it's n groups, I think. And so, yeah, so that functionality is built in. I just don't have time to cover all the parameters. The second question was ODBC. And so one of my former colleagues, Joel Bernstein, has been doing a lot of work doing SQL for Solr 6. And how I understand it is that you can point it at you could it will work over either like streaming Solr, or you can also point it at the new facet module through the JSON facet API, and it can also work off that. So I guess the short answer is, yeah, we're doing a lot with SQL, and but go see Joel's presentation too. That'll have a lot more. Yes.
Yeah, I was wondering for the new facet module, is it use it for any version of Solr, or what versions of Solr can we use it for?
Well, the first versions that it was in were like 5.1. But I've been building on it since, so each version has more functionality than the last one.
Okay, and then is there plans to have that like no longer be a module and just have it baked into the Solr?
It is baked in.
Okay.
It's just a name.
Gotcha. Okay.
I was just trying to distinguish it from the existing facet stuff. So the name I used was new facet module, but it's there, and it's less like a module because it's very highly integrated. Yes. Yeah.
So as one question is about the top docs. You're talking the top docs basically. Actually, we using Solr. I mean, we realize you mentioned the issue. Basically, once you start using Solr for searching, basically you couldn't go back to database anymore. So that's why we're forced to use analytics with Solr. So that's a challenge for us is with the traditional SQL, it can do all kind of group by thing, right? So basically for Solr we do grouping too, and then you run into challenge that I couldn't just sort by any field by such thing, right? Because this grouping only provide a default sort which is relevancy, right? Maybe count, I'm not sure, relevancy only. So is there any such a plan to improve the grouping results, like sorting by any field, by any kind of a function?
So the question was, the short form I think is, what can we sort by, and are there plans to offer increasing things, you can sort by, and yes, like the new facet stuff can already sort by any kind of statistic you can compute. It can sort by count ascending if you really want that. Some people have asked for that in the past, and yeah, we're going to just continue the number of things that we can both calculate and sort by.
But this new facet, it doesn't relate to the group by that.
It's not. It'll get there. I think the new facet module will have eventually all of the functionality that the current grouping module has.
Great. A second question, and when you compare the performance between the pivot faceting and your new faceting, the indexing format is the same. So our question is whether this what they call doc values actually more helpful to this new facet module.
I think the question was would doc values be more helpful to the new facet module as it relates to the benchmarks? I don't think that would have had the impact. I think most of the performance impact is from the statistics module. Once we already retrieve the value, what do we do with it? How efficient is that process? And I see that we are out of time, but I can take more questions outside. Well, thanks.
Thank you.